push that up and then here's green. Mustn't forget the online audience.
I'll do that for everybody.
Oh, Stephen's sitting beside you.
Yes, he is.
I didn't see him there.
Well, that's great. Oh, maybe it's now it's working. Okay. Thank you, everybody. Martin Frankland is going to speak on enriched model categories in the Dold-Kan correspondence. I apologize for coming in late here. I still trying to change money.
Thank you. First, I'd like to thank the organizers for this opportunity to speak and for putting on this great conference in memory of Fred Cohen. I've met Fred a few times at conferences, didn't know him closely, but the few times that I did meet him, he always struck me as a gentle soul, always positive, always optimistic, despite having some health challenges. And of course, his mathematics was superb as well. In particular, for my work, his work on the homology of iterated loop spaces was influential. Notably, the monograph, Cohen-Latame, was very helpful when I was trying to learn about Dyer-Lashoff operations and power operations. So I'm thankful for that. The project I want to present today is in a different part of homotopy theory. It's all joint with Arnaud Gopnan-Gompé, who is my PhD student. And in fact, this is part of his doctoral work that we're writing up as a joint paper. So for now, if you're curious to hear more details, you can look them up in his thesis, which is on my website. The preprint, the version is not yet available. And then in his thesis, some of the main references, just for background, are Schwede and Shipley, equivalences of monoidal model categories. That was very influential for this work. And then background references on model categories, Mark Hovey's book, May Ponto, concise course, more concise course, and Emily Reel's categorical homotopy theories. Fantastic resources for what I'll talk about. All right, let's jump in. Let's recall some very classical facts about the Dold-Kan correspondence. How does that go? Well, if I give you a simplicial module, just to simplify things, let's say R is a commutative ring for today. A bit more general, but that's enough for our purposes. And you take a simplicial R module, simplicial R modules. You can normalize your simplicial module. It's the normalization functor, and it gives you a non-negatively graded chain complex of R modules. Chain complex, non-negative degree of R modules. And that's an equivalence of categories. So I'll denote by gamma the inverse, the denormalization. This is an equivalence of categories, although being an equivalence of categories is not really relevant for what I'll talk about, but it happens to be true in this case. That's the normalization. And that's the denormalization. For instance, if you normalize the constant simplicial module, you end up with just the module in degree 0 and nothing else as a chain complex. All right, not only is it an equivalence of categories, it has interesting monoidal properties. So what about the monoidal properties? Well, both sides are lax monoidal. If you prefer, if you put everything on the normalization side, normalization is lax monoidal via the Eilenberg-Zilber map, also called the shuffle map, because the formula involves shuffles. I'll call it Eilenberg-Zilber. Goes this way. If you take two simplicial modules, you normalize both of them and take the tensor product of those chain complexes. There's this natural map comparing those two sides. And even better, you can go backwards. Normalization is also lax monoidal, or also called lax co-monoidal. The the Alexander-Whitney map going the other way. Alexander Whitney is a diagonal approximation. It's trying to break up something into something diagonal into horizontal and vertical pieces, so to speak. And this complex is actually a deformation retract of this one. This one is smaller, this one is bigger. More precisely, if you first start here, go into the bigger one, and go back, that was a retract. So that was a retraction. If you first Eilenberg-Zilber, then...
Why is half of the parentheses straight line?
Ah. Oops. Oh, yeah, that parenthesis is not round enough. I agree with that. All right, it is a parenthesis. Yeah, it was not a slash. All right, so if you Eilenberg-Zilber and then Alexander Whitney back into the tensor product of chain complexes, you went back where you started. The other way around from the big complex down to the small one, and including, is chain homotopic to the identity, naturally chain homotopic. That's chain homotopic to the identity. So for the tech aficionados, that's sim x, not an equal. That's chain homotopic. My favorite example is just to, I can't resist the urge to mention that. Just think of this tiny example. It's the smallest example where you really see why this is not equal. Think of just a normalization of delta 1, the free abelian group on delta 1, sitting inside a square. That's the tensor product of those simplicial modules. And already, well, in degree 1, that's a free abelian group of rank 4, whereas this has 5 one simplices. And in degree 2, this one has only 1 2 simplex, just one copy of Z, and this one has 2. So this is definitely smaller than that. All right, that's all very classical. We're going to do homotopy theory with those functors, not just the monoidal properties. We need the homotopical properties. Both are equivalent equivalences, or more precisely, because it's an equivalence of categories, I can think of it as an adjunction in 2 ways. I can pick either functor as my left adjoint, and both will be equivalent equivalences. With respect to, let's say, the projective model structure on chain complexes and the standard model structure on simplicial modules, that's right induced by along the forgetful functor to simplicial sets. So this, the pi star isomorphisms as weak equivalences. That is getting closer to our purposes. The fact that they're equivalent equivalences is really more than what we need. The fact that they're equivalent pairs is crucial to what we need. And the main issue is that neither direction is strong monoidal. So those 2 sides, I mean, they're not even isomorphic, let alone naturally. But it's the next best thing is true. They're strong monoidal up to homotopy. This circ is a composition, yes. N gamma. Oh, sorry. The turnstile here is just a junction. If I think of the normalization as the left adjoint of this adjunction, or as the right adjoint, in both cases I get equivalent equivalence. That's what I meant. Thank you. All right. Both functors are. Allow me to use a colloquial description, and the point of the next definition will be to make that precise. They're a strong monoidal up to homotopy. More precisely, can I jam that in here? Let's give it a try. All right, this key observation of exactly the right properties that we need, that goes back to Schwede and Shipley, this paper, Equivalences of Monoidal Model Categories. They just pin down the ingredients that make this work. It's a weak monoidal equivalent pair. Well, it better be a equivalent pair, otherwise that would be misleading. It's a equivalent pair. And I'll use the same generic notation for the rest of my talk. So let's just call the adjoints F and G. And for reasons I'll explain in a second, I'll denote the categories script W and script V. And I want both of them to be monoidal model categories. I'll recall what that means in a minute, but just bear with me. Yeah, actually that belongs here. That's part of the basic setup. V and W have to be monoidal model categories. Sorry for the word work here. All right, V and W are monoidal model categories, and we want to compare their homotopy theories in a way that takes into account the monoidal structure. So what do we assume? Let's go over here. What we want is the right adjoint to be lax monoidal. By doctrinal adjunction that corresponds to an opt-lax monoidal structure on the left adjoint. It's just a little commutative square. I just like to say doctrinal adjunction as often as possible. Corresponding opt-lax monoidal structure on the left adjoint. That's the one that should be strong monoidal up to homotopy, namely, what's the philosophy of homotopy theory? We start with isomorphisms and just weaken them to weak equivalences that satisfy some coherence. That's exactly what we'll do. The co-multiplication not assumed in isomorphism, that would be part of being a strong monoidal. But next best thing is true, it's a weak equivalence when it's homotopically meaningful, namely when both objects are cofibrant. And likewise with the co-unit map. Well, let's see, the co-unit map has this shape. It's f of the tensor unit going to the tensor unit, the other category. So bold 1 is my tensor unit. That's the tensor unit in W. That's the tensor unit in V. And I don't want to require that to be an isomorphism yet. I will in a few minutes, but for now, let's see. Oh, right. So let's see, what do I want to require? Yeah, okay, let's do this instead. We want to say that if you cofibernally replace the tensor unit, I'll denote that by Q of 1. That's a cofibrant replacement. It's called little q, the cofibrant replacement map. Apply F to it, and then apply this co-unit map. Really, that's the one that should be a weak equivalence. That's the only map that actually matters here. You don't require that either individually be a weak equivalence. Okay, so we've weakened the conditions of being strong monodal to a homotopical condition instead. And the main example is Dold-Kan, again in either direction. So the motivational example is, well, Dold-Kan. Both thinking of the normalization, this left adjoint, and thinking of it as a right adjoint. Both will satisfy this definition. All right. So that's the setup for the question we want to look at. In fact, their focus in this paper was to study the homotopy theory of monoids in both categories. So Schwede and Shipley wanted to understand monoids in both categories, so they needed a little bit more. They needed a monoid axiom to have a good homotopy theory of monoids, but that's not relevant to our purposes. In particular, in this motivational example of Dold-Kan, if you take monoids on both sides, what do you get? You get simplicial R algebras versus DG algebras over R that are non-negatively graded. One of the results from their paper, one of the main results, is a correlative equivalence between those two sides. Simplicial R algebras, simplicial algebras over R are correlate equivalent to DGAs, differential graded algebras over R. My DGAs for now are non-negatively graded, so really both sides are just monoids. Those are the monoids in simplicial modules, and those are the monoids in non-negatively graded chain complexes. Great. So we start from the same key observation, those properties, the lax monoidal equivalent adjunction, but we go in a different direction. The problem we look at is what happens if I change the enrichment along such an adjunction. If I started with a homotopy theory that's enriched, let's say in simplicial modules, and I decide to just normalize each Hom space, what kind of structure do I get? Or vice versa. I start with a DG category and I start denormalizing the Hom complexes. And let's do that over here. Oh, correlate equivalence. Thank you. Yeah. So those two model categories are correlate equivalent. In the case of Dold-Kan, it turns out that both sides are induced by the original functors, but in their more general theorem, you got to be very careful. The left adjoint becomes totally different. It's the monoidization of the original left adjoint. Anyway, you can look at the paper for more details. All right. Our focus is going in a different direction. Yeah, so in this setup, R is any, say, commutative ring, so it could be Z in particular. I'm not assuming commutative algebras. That's where it's totally different. You'd want a Q algebra, for instance. or switch to E infinity. For the commutativity, so the symmetry properties, there's a beautiful paper by Dold-Kan working out exactly all the symmetry conditions. It's not really crucial to our purposes, so I will not be using that. By change of enrichment, it's also called change of base, because you just change the base of the enrichment by applying a lax monodal functor to each Hom gadget. If you had Hom spaces or Hom complexes, whatever, just apply the lax monodal functor locally. That's what I mean. So yeah, so just to recall what I mean by change of enrichment, if you have the category that's V enriched, changing the enrichment will be denoted with G star. And it's going to be W enriched. Again, a very classical construction. It's described in Kelly's Basics of Enriched Category Theory, for instance, or Bourseau, Volume 2, beautiful reference. I'll denote G star, where the Hom gadgets are just the original Hom gadgets to which we've applied G. So in symbols, what if I want the Hom gadget from X to Y? After changing the enrichment, I just apply G to the original Hom gadget. Let's parse this formula. That was originally living in V, but now I'm changing the enrichment to something that lives in W. And composition is just induced by applying G to the original composition and using the lax monodal structure. That's where it's crucial. All right. Oh, I tend to underline when I mean the enriched version. I may forget, but I like underline to stress that we're dealing with an enriched Hom gadget, not just a Hom set. And before I state our main result, I need a bit more background. Just bear with me. Let's review some background about enriched model categories. I promise to recall the definition of monodal model category. Here we go. Well, it should be both a model category and monodal in a compatible way. All right, what do we need? I'll assume that it's closed, so it's got internal Homs, that it's symmetric monodal, so that I don't have to stress about swapping some tensor factors occasionally. All right, that's just the monodal part. What about the model part? It's equipped with a model structure. Oh, I'm dangerously close to the line of sight. I need compatibility between those two pieces of structure. It comes in the form of two axioms. You want the tensor product to be equivalent bifunctor. So that's fancy words, just meaning the following condition, also called the push-out product axiom. You start with a cofibration I. And P fibration. The map from the push-out product, let me just recall how that works. You tensor the two things separately and then use the maps in the only possible way you could use them. Oh, I'll write my tensoring on the right. All right, so here I can use, let's say, I in the second tensor factor. Or I can decide to use P in the first factor, tensor factor. And then I can do it the other way. So I get a map, a natural map out of the push out here. Well, okay, I'll run out of space here, but let's just say the map induced out of the push out. Oops, sorry, that was a side remark. I'm back in the main text now. This map right here, which is usually denoted I box. Oh, no, sorry, that's my P box I. Should be. Oh, sorry, I'm thinking of the. I'll give some equivalent. Yeah, equivalent conditions. In this version, both are cofibrations. They both have the same variance, and I want that to be a cofibration. Basically, if either, yeah, so P is horrible notation. That should be a J. Now that's less horrible. All right, much better. Right. I'll give some reformulations that will be useful in a few minutes. And then there's the unit axiom. Right, this is saying that the tensor product plays nicely with the homotopy theory. And now you want the tensor unit to play nicely with the homotopy theory. That's called the unit axiom. All right, you'd like to say that the tensor unit is a tensor unit up to homotopy somehow. But that only makes sense if you tensor cofibrant things. So the axiom forms takes this form. If you tensor with a cofibrant replacement of the tensor unit, that should be weak equivalence. Well, X is cofibrant, so this is homotopically meaningful. And this was just the identity tensor, this cofibrant replacement map for the tensor unit. All right, that's a monoidal model category, and many examples that you see in day-to-day life do satisfy this. Topological spaces, or convenient topological spaces with a Serre model structure, simplicial sets with a Conquilin model structure, or pointed spaces, pointed simplicial sets with a smash product. That's all good. Oh, let's move on to things that look more like Dold-Kan. Model categories we were looking at a few minutes ago also satisfied these conditions. Unbounded chain complexes as well. I like stable homotopy theory. I think some of you do as well. Various categories of spectra satisfy that. Symmetric spectra of simple shell sets. Orthogonal spectra, and so on. There are also some non-examples. It could happen that a model category happened to be monoidal, but without satisfying this. You see those kinds of examples less in algebra and more in higher category theory. There you got to be extra careful. That's just a rule of thumb. That was not a theorem. All right. So we've got plenty of monoidal model categories. Now we want to talk about enriched model categories. The model category is a category, say script C, that is enriched, tensored, and cotensored over V. Tensored is also called co-powered. It just means that you can tensor from the outside from an object of V. For instance, the usual tensoring over sets is just taking a big co-product of copies of the object in C, indexed by the set. Let's see, enriched, tensored, and cotensored over V. So far, that's just a monoidal part. I want some homotopy theory, so I assume that there is a model structure on the underlying category. A model structure that is on the underlying category. For any monoidal category V, there's an underlying set, which is just the Hom set from the tensor unit. So any monoidal category comes with a canonical forgetful functor to sets. And in particular, any V-enriched category has an underlying category by changing the enrichment along the forgetful functor. So that's what I mean here, by underlying category. I mean, there's this whole debate in the enriched homotopy theory community whether V-enriched category should be viewed as a noun, or it starts life as being V-enriched, and that's all it is. It happens to have an underlying category, or it should be viewed as an adjective. You start with a category and put extra structure on it, which is the V-enrichment. I'll use the latter perspective. So really, I want to think of the underlying category as being the thing we start with, and it happens to come with this extra structure of an enrichment.
And the model category structure is on the first enrichment as well?
So good question. So the model structure is on the underlying category, but it will have to be compatible with the enrichment in a sense that I'll write down now. So if you like, I'll make up notation for underlying C. Right, so far we just have the two pieces of structure. What is the compatibility? Well, just copy paste those two definitions and think of one of the variables as coming from V instead of C itself. So let me call that the external push out product axiom. To save time, I won't copy paste it, but I ask you to copy paste in your mind and change the few words that need to be changed. Okay, just to be more precise, my I from A to B would be taken from V, and my J would be coming from C. And then this diagram makes sense because I have a tensoring right on the right. Okay. And the statement is identical from that point. And likewise, you can write the external version of the unit axiom. Same deal. In the external version, I'm tensoring from an object in C with an object in V. And now this is the tensor unit in V that I cofinitely replaced in V. Oh, so this might be familiar. We all love Quillen's work, and that should look like SM7. But if you look up Quillen's homotopical algebra from '67, SM7 takes a different form. And that's very convenient because this form requires the tensoring, which we will lose in a few minutes. I have till, okay, yeah, which we will lose very soon. Yeah. You can reformulate this external push-out product axiom following our equivalent in the setup we're looking at. External push-out product axiom, that's phrased in terms of tensoring. If you're allowed to tensor with objects in V, you can write down this map. And there's a dual version where you use the co-tensoring. To save time, I won't dwell on that. They come in pairs and they're dual to each other. But that's the external pullback power axiom. Just think of dualizing this picture, but you use the co-tensoring everywhere. This uses the tensoring. This uses the co-tensoring. The more interesting one is SM7, which uses the enrichment only. So I've been calling it, this version, EM7 in my head for enriched model categories as generalized SM7, but I'm the only person in the world calling it EM7, so I'll stick to SM7. But it's just a generalization to other monoidal model categories than simplicial sets. That was for simplicial model category. So really, for those keeping track, that's a generalization, but it's the same definition. That uses the enrichment. How does it go? Let's do a bit of scratch work. It's just telling you that the space of lifts lives above the space of lifting problems. Right, in the model category, you've got lifting problems like that. Then you're looking for a lift. And in a just plain model category, you can find a lift if either side is acyclic. And SM7 jazzes that up to a space of lifting problems and the space of lifts. In other words, space of all possible lifts lives over the space of lifting problems. So compose with with P. Look at this pullback. This pullback right here is exactly the space of lifting problems. It's giving you two maps like that that make the square commute. And this is a fibration. Acyclic if either I or P is. So my I was a co-fibration, my P was a fibration. All right. So we have all the ingredients to state the main theorem. Well, almost up to defining a few words, which I'll do in the remaining time. Main result, that chapter of Arnaud's thesis, is that in the setup above, you start with a V model category. Well, okay, I'll write that part. Oh, you know what? Before I do that, let me first go to the well-known fact when things go well. The well-known case was when F is strong monoidal. Let me regret this in 30 seconds. All right. So if F is strong monoidal, or rather if the whole, if the whole equivalent pair is strong monoidal, then things go as well as they could. C is a V model category. Then you change the enrichment along that right adjoint, and you canonically get a W model category. So all the ingredients just go through as you would hope. Statement is found, for instance, in Emily Riel's book, but it goes further back. I think some pieces were in Javi's book already. All right, so the whole project was to say, well, what if we drop this assumption? What's left? And I can tell you. Well, okay, now I need to be more precise because the setup above is not the one I want. If the equivalent pair is weak monoidal, I do need a bit more. I need to assume that F has one of the two conditions of being strong, namely preserves the tensor unit. That will be convenient. A mild condition, it's satisfied by Dold-Kan. C is a V model category, then changing the enrichment will give me a weak W model category. So changing the enrichment will yield this W enriched category. It's a weak W model category. Now you may complain that there's as of yet zero content to this statement. Maybe I just define this word to mean a category obtained of that form. So in the remaining few minutes, I'll sketch what ingredients we need in here. We just coined this definition so that by design it makes the theorem true. But the actual content is coming. All right, let's go through the ingredients. Oh, and in fact, the definition was, again, motivated by this statement, but it turns out after the fact that if you, again, change the enrichment from a weak model category, you get a weak model category out of that. It saturates after one step. You don't lose more after repeating the process. All right, well, let's see. In a V model category, what are the ingredients? We need an enriched category, right? What are the ingredients that go in there? There's the enrichment. And what happens when you change the enrichment, right? Well, we still have an enrichment, right? We're just changing the enrichment along a Lax-Monodal functor. No problem there. We need tensoring and co-tensoring, and that's where all the hard work is. So I'll keep that for later. Let's look at the model structure. To save time, I'll just state this proposition. It turns out that this right adjoint G will preserve the underlying set if and only if its left adjoint preserves the tensor unit. So here we just use the lazy way out and put that assumption in so that the underlying category hasn't changed. Just keep the same model structure. So this is where we assume this extra hypothesis, which is there to guarantee that the underlying category is the same. It's true for Dold-Kan. It's true for the singular set. What about, say, geometric realization is a famous example that does not preserve the underlying set. Right? Start with delta 1. Its underlying set has 2 points. Geometrically realize the underlying set is uncountably infinite. It's huge. So some functors just don't preserve the underlying set, and this one will. So we're good with that assumption. We just keep the same model structure. Then we want SM7. The good news is that this one just goes through. It's fine. And I'm using the form that only requires the enrichment, because I have that. SM7 just requires an enrichment. The thorny issues are the tensoring and co-tensoring. And then the unit axiom. And the remaining, like two minutes, I guess. So this is not preserved. In fact, provably so. In this known case, how do you get the induced tensoring and co-tensoring? By the only reasonable way you could, namely, how do I act by a little W on my objects in C? I just use F to go back to F and use the original tensoring. It's the only formula you would guess for an induced tensoring, and it works. Here, it just doesn't work. And in fact, so G star C admits a tensoring or a co-tensoring over W if and only if the left adjoint preserves the tensor unit. So we weren't just being extra careful. You really need that condition. So here you provably lose it, but it's not fully gone. It's actually weakened. Get a weak tensoring and co-tensoring. And then for the unit axiom, it turns out that there are a few equivalent ways of phrasing it. Again, to save time, I'll just tell you the 3 ways. One way was the one I wrote down, where you take cofinitely replace the tensor unit and tensor a cofinite object, and you get a weak equivalence. You can rephrase that by the condition that we like to call the pi0 of mapping space condition. I'll pull Fred Cohen, just cover the board. So this pi0 of mapping space condition says that you can compute the Hom set in the homotopy category by using the homotopy classes from the tensor unit into the mapping gadget, mapping space. So that's equivalent to the tensor, the unit axiom. And then there's the detection property, which says that if I have a map between cofibrant objects and I want to know, is this a weak equivalence? You test it by harming into fibrant objects. And if you get an equivalence of mapping spaces, then the original map was a weak equivalence. You can detect weak equivalences that way. And those three conditions are equivalent: unit axiom, pi-0 mapping space, detection property. Except that's assuming that you had the tensoring and co-tensoring. If you jettison the tensoring and co-tensoring, all we were able to prove is that unit axiom implies pi-0 of mapping space, implies detection property. And the change of enrichment preserves the first two and preserves this one under some mild additional assumptions. So the point here is that we're okay up to being careful about which form of the unit axiom you're using. It goes through. And just to conclude, let me just 30 seconds write a small application. Comparing enrichments. Let's say I work in chain complexes, but I want a mapping space. I would like a simplicial set of maps. Take two chain complexes. Well, you can use Dold-Kan locally. Just first look at the internal Hom in there. So concretely, that's the usual Hom complex, but truncated in degree 0 to land back in here. So that's the internal Hom in there, and then denormalize the whole thing. That's a simplicial module. You can also use Dold-Kan globally. Just transport the whole thing over to simplicial modules, and then use the mapping space in there. And my master student, Michael Opadoton, showed that there's a natural homotopy equivalence of simplicial modules between those two induced by Dold-Kan. He proved it more or less directly using a calculation. And then that got me thinking there's got to be something in the background going on. And a nice, maybe conceptual reinterpretation is that we've just changed the enrichment along the denormalization. And now this has a weak co-tensoring. So this is the change of enrichment. We just apply denormalization locally to each mapping gadget. Versus this is the co-tensoring. That's the weak co-tensoring that you get from the theorem. Weak co-tensoring of chain complexes over simplicial modules. That's the co-tensor by a simplicial module acting on a chain complex. So thank you for your attention.
Thank you. May I say this was a very rich lecture.
Thank you.
That was really something Tony should have said.
Well, I am enriched.
Okay.
Glad to hear it.
Any questions?